Right now, a frozen world sits 4.5 billion kilometers away. Neptune, the solar system's outermost giant, a planet so distant that sunlight takes over 4 hours to reach it. We sent one spacecraft there in 1989. It took 12 years. But that was just a flyby lasting mere hours. What if we wanted to stay? What if we wanted to send humans? Scientists have calculated the journey times. They have designed the propulsion systems. They have solved the distance problem on paper. But there is something they cannot solve. Something that breaks every mission plan ever conceived. The machines themselves are dying. Not from impacts, not from radiation, from time. If you are ready to discover why the final frontier might remain forever closed, tap that like button and subscribe. Now, settle down and get yourself comfortable. Let's begin. Something extraordinary happens when you travel beyond Mars. The solar system transforms from a neighborhood into an abyss. The distances between worlds stop following patterns that human intuition can grasp. They become something else entirely. Something that breaks every assumption we carry about travel, about technology, about what machines can endure across the merciless passage of time. Mercury orbits the Sun at roughly 58 million kilometers. Venus circles at 108 million. Earth maintains its position at approximately 150 million kilometers from the burning center of our cosmic neighborhood. Mars extends outward to 228 million kilometers. These inner worlds cluster together in astronomical terms, separated by gaps that spacecraft can cross in months or even weeks with favorable orbital alignments. The distances remain comprehensible. A journey to Mars takes roughly 7 months with current propulsion technology. Astronauts could theoretically survive such a mission, using systems already demonstrated aboard the International Space Station. Then comes Jupiter, 778 million kilometers from the Sun. The gap between Mars and Jupiter exceeds the combined distances from Mercury to Mars several times over. This is not a gradual expansion of the solar system. This is a sudden leap into vastness that changes everything about how we must think about exploration. Saturn doubles Jupiter's distance again, orbiting at 1,427 million kilometers. Uranus pushes the boundary further still, maintaining an average orbital distance of 2,870 million kilometers from the Sun. Each successive world demands exponentially longer journey times. Each world sits in deeper cold, receives less solar energy, exists in greater isolation from the warmth that makes Earth habitable. And then comes Neptune, 4,495 million kilometers. The number requires 13 digits to write in standard notation. Spelling it out in words barely helps comprehension. 4 billion, 495 million. Kilometers. Each kilometer containing 1,000 meters. Each meter stretching roughly the height of a tall human standing on another's shoulders. The mind grasps individual units while losing entirely the meaning of their accumulation. The human brain evolved to process distances measured in footsteps. Our ancestors needed to judge whether prey was close enough to chase, whether predators were far enough to ignore, whether water sources lay within walking range. The savannah rewarded accurate distance estimation across hundreds of meters, perhaps across a few kilometers for those tracking migrating herds. Nothing in our evolutionary history prepared us to contemplate distances measured in billions of kilometers. The numbers become abstract. They lose meaning. They transform into symbols that our minds acknowledge without truly understanding. Perhaps a different approach helps establish scale. Light travels at approximately 299,792 kilometers per second. Nothing in the universe moves faster. This represents the ultimate cosmic speed limit, embedded in the fundamental structure of spacetime itself. At this inconceivable velocity, light leaving the Sun requires roughly 8 minutes to reach Earth. That same light needs approximately 4 hours and 10 minutes to reach Neptune. When astronomers observe Neptune tonight through their telescopes, they see the planet as it appeared over 4 hours ago. The present moment Neptune remains forever hidden behind this temporal barrier imposed by the finite speed of light. Consider what this means for communication with any spacecraft we might send to Neptune. Radio signals travel at light speed. A message transmitted from mission control on Earth to a spacecraft orbiting Neptune would require over 4 hours to arrive. Any exchange of information would span more than 8 hours for each round trip. Real-time communication becomes physically impossible, regardless of how powerful our transmitters or how sensitive our receivers. Instructions sent from Earth would describe situations that existed hours ago. Responses would arrive hours after circumstances had changed beyond recognition. If you could drive a car at highway speeds toward Neptune, maintaining 100 kilometers per hour, without stopping for fuel, rest, or maintenance, the journey would require over 5,000 years. Entire civilizations have risen and fallen across shorter timescales. If you could walk continuously without rest, moving at 5 kilometers per hour, you would need roughly 100 million years to arrive. Complex life had barely emerged from the oceans when your walk would have needed to begin. These comparisons illuminate the absurdity of Neptune's distance from any human perspective, yet they only hint at the deeper challenge that makes Neptune exploration fundamentally different from anything humanity has previously attempted. This communication delay represents merely the first hint of what Neptune's distance truly means for human exploration. The deeper implications emerge when you examine how long it takes to physically cross such distances, with actual spacecraft using actual propulsion systems that exist or might feasibly be developed. One spacecraft has successfully visited Neptune across the entire history of human technological civilization. Voyager 2, launched from Cape Canaveral on August 20th, 1977. Its mission exploited a rare planetary alignment that would not recur for another 175 years. This cosmic coincidence, sometimes called the Grand Tour alignment, allowed a single spacecraft to use gravity assists from Jupiter, Saturn, and Uranus to reach Neptune without the enormous fuel requirements that a direct trajectory would demand. The journey consumed 12 years. Voyager 2 departed Earth when disco dominated radio stations, when personal computers remained exotic novelties. When the Soviet Union still existed as America's Cold War rival, the spacecraft crossed the solar system while human society transformed around the absent travelers who had launched it. Children born the year of launch were entering adolescence when Neptune finally appeared in Voyager's cameras. Adults who had celebrated the launch as young professionals were approaching middle age when the encounter finally occurred. When Voyager 2 reached its destination on August 25, 1989, it transmitted photographs of a world that defied all expectations formed from studying the other giant planets. Scientists had assumed Neptune would resemble a dimmer, colder, more quiescent version of its neighbours. They expected a world where distance from the Sun had slowed all processes to torpid equilibrium. Instead, they discovered a planet of violent atmospheric activity that seemed to mock its frozen isolation. Winds exceeding 2,000 kilometers per hour tore through Neptune's atmosphere, making it the windiest planet in the solar system despite receiving only 1/900th of the solar energy that reaches Earth. This paradox suggested internal heat sources, driving atmospheric dynamics in ways that solar energy alone could not explain. A massive storm system dubbed the Great Dark Spot dominated the southern hemisphere, rotating counterclockwise with ferocity, rivaling Jupiter's famous Great Red Spot, despite Neptune's far smaller size and far colder temperatures. Neptune's largest moon, Triton, proved equally surprising and scientifically valuable. Its surface displayed geological features suggesting active processes continuing into the present day. Geysers of nitrogen gas erupted from the frozen terrain, shooting dark material several kilometers into Triton's thin atmosphere. The Moon orbited backwards relative to Neptune's rotation, moving in a retrograde direction that suggested capture from the distant Kuiper belt rather than formation alongside its parent planet from the same primordial disk of gas and dust. These discoveries revolutionized planetary science. They revealed that the outer solar system contained worlds of unexpected complexity and ongoing activity. They demonstrated that distance from the Sun did not automatically mean geological death or atmospheric stagnation. They proved that Neptune deserved intensive study across extended time frames to understand processes that brief encounters could only glimpse. But here is what most accounts of the Voyager encounter omit: the detail that transforms Neptune from a challenging destination into an effectively impossible one for human explorers. Voyager 2 spent approximately 12 hours in close proximity to Neptune. After traveling for 12 years across billions of kilometers, the spacecraft captured its photographs, collected its measurements, transmitted its discoveries back to Earth, and continued onward into interstellar space without slowing. It never entered orbit around Neptune. It never lingered to study seasonal changes or track storm evolution over months or years. It never deployed instruments to Neptune's surface or its moons. It flew past at tremendous velocity and kept going, disappearing into the outer darkness where it continues traveling today. This was not a mission design, oversight, or a failure of scientific ambition. This was the only mission profile that remained viable after 12 years of deep space operations. The brief flyby was not a choice. It was a necessity imposed by the accumulated toll that 12 years had taken on the spacecraft. By the time Voyager 2 reached Neptune, the spacecraft had already experienced significant degradation across multiple systems. Its instruments had been operating continuously for over a decade in conditions that included extreme temperature variations between sun-facing and shadow-facing surfaces, constant cosmic ray bombardment that damaged electronic components with every passing month, and the accumulated mechanical stress of operations far exceeding original design specifications. Several backup systems had failed during the journey. Primary systems showed declining performance across multiple metrics that mission controllers tracked with growing concern. Had mission planners attempted to slow Voyager 2 for orbital insertion around Neptune, the required engine burns would have placed extraordinary demands on propulsion systems that had already operated far beyond their intended lifespan. Fuel valves that had remained closed for years would need to open reliably. Combustion chambers that had cooled to cryogenic temperatures would need to withstand sudden heating. Attitude control systems would need to maintain precise orientation during burns lasting many minutes. The probability of successful orbital capture remained uncomfortably low, given the age and condition of critical components. The probability of catastrophic failure during deceleration burns remained uncomfortably high. Mission controllers chose the safer option: a fast flyby that maximized scientific return from the encounter while minimizing demands on aging systems. They accepted 12 hours of close observation rather than risking total mission loss, attempting orbital capture that degraded systems might not survive. This decision illuminates a truth that most popular discussions of space exploration prefer to ignore, a truth that transforms how we must think about Neptune and destinations beyond. Every spacecraft begins dying the moment it leaves Earth. This is not poetry or dramatic exaggeration. This is confirmed physics operating through mechanisms that affect every material, every component, every system that human engineers have ever built or conceivably could build with known science. Metals fatigue under repeated stress cycles, developing microscopic cracks that propagate with each thermal expansion and contraction. Lubricants evaporate in vacuum or break down under radiation exposure, leaving mechanical systems grinding against each other with increasing friction. Electronic components accumulate damage from cosmic ray impacts that flip bits in memory systems and degrade transistor performance. Seals harden and crack as polymer chains break under ultraviolet exposure and particle bombardment. Batteries lose capacity as electrode materials deteriorate through charge-discharge cycles. Solar panels degrade as radiation damages photovoltaic cells. Radioisotope power sources decline according to immutable nuclear decay curves that no engineering can alter. Nothing in a spacecraft lasts forever. Nothing even lasts as long as Neptune missions require. Modern spacecraft engineering has become extraordinarily sophisticated at delaying this inevitable deterioration. Engineers select materials that resist specific degradation mechanisms relevant to their mission environment. They design redundant systems that can compensate when primary components fail. They test every assembly under simulated space conditions for months or years before launch, identifying weaknesses before they cause mission-ending failures. They build margins of safety exceeding mission requirements by factors of 2 or 3 or more. These techniques enable missions lasting years with acceptable reliability. They have supported the International Space Station for over 2 decades through continuous maintenance, regular resupply, and component replacement impossible for deep space missions. They have kept the Voyager spacecraft transmitting scientific data for over 46 years, though with progressively reduced capabilities, repeated system workarounds, and the gradual shutdown of instruments that can no longer be powered or no longer function correctly. But these techniques cannot stop time. They can slow the accumulation of damage. They cannot prevent it entirely. Every day of operation adds incremental degradation that eventually accumulates beyond compensation. This brings us to the central truth that dominates any serious technical discussion of Neptune exploration. The fundamental challenge is not crossing the distance. With sufficient propulsion, any distance can theoretically be crossed. The fundamental challenge is keeping spacecraft systems functional long enough to complete the crossing, while maintaining conditions that sustain human life. Current chemical propulsion technology, the same basic approach that carried Apollo astronauts to the Moon over 50 years ago, would require approximately 12 to 15 years for a crewed mission to reach Neptune. That estimate assumes a direct trajectory without orbital insertion at the destination. Essentially a repeat of Voyager 2's mission profile with human passengers rather than robotic instruments. The crew would fly past Neptune, observe it briefly, and continue outward into space because stopping would require additional years of travel time to set up approach trajectories that allow orbital capture. If mission planners wanted to actually stop at Neptune, to enter stable orbit around the planet, to conduct extended scientific operations lasting months or years, to eventually return the crew safely to Earth, the mission timeline extends dramatically. Orbital mechanics demand significant fuel expenditure for deceleration. The most efficient trajectories that minimize propellant requirements also maximize travel time, potentially extending journeys to 20 or even 30 years for complete round-trip missions, including substantial time at Neptune for scientific observations. Consider what a 30-year mission means. Astronauts would launch in their 30s and return in their 60s. They would miss their children's entire childhoods. They would miss their parents' final years. They would return to an Earth transformed by 3 decades of technological, political, and social change. They would need to remain healthy, functional, and psychologically stable across timescales that exceed most professional careers. Nuclear thermal propulsion could theoretically reduce these journey times by perhaps 30 to 40%. This technology was tested during the 1960s and early 70s before congressional budget cuts terminated development. The fundamental concept uses a nuclear reactor to heat hydrogen propellant to extreme temperatures, achieving exhaust velocities roughly twice what chemical rockets can manage. Modern interest in reviving nuclear thermal propulsion has produced design studies, component testing, and congressional authorization for development programs. But no flight-ready nuclear thermal engines exist today. None have been tested in space. Development timelines stretch across decades, even under optimistic funding assumptions. Ion propulsion and other electric propulsion systems offer dramatically higher fuel efficiency but much lower thrust, making them better suited for cargo delivery than crewed missions, where journey time directly impacts crew survival. The Dawn spacecraft used ion propulsion to visit Vesta and Ceres in the asteroid belt, demonstrating the technology's potential while also revealing its limitations. Acceleration with ion drives proceeds so gradually that journey times extend rather than contract for many mission profiles, where the efficiency advantage cannot compensate for lower thrust. Various exotic propulsion concepts populate theoretical literature and science fiction narratives. Nuclear pulse propulsion would detonate atomic bombs behind a spacecraft for acceleration, potentially achieving tremendous thrust at the cost of radioactive contamination of the launch area and violation of international treaties prohibiting nuclear explosions in space. Antimatter engines could theoretically achieve extraordinary performance if anyone could produce and store antimatter in quantities beyond the few atoms that particle accelerators occasionally create. Laser propulsion could accelerate lightweight sails to velocities approaching a significant fraction of light speed, but offers no mechanism for deceleration at the destination, making it useless for missions that intend to stop rather than simply fly past. None of these exotic concepts have advanced beyond paper studies and laboratory experiments. Practical implementation timelines stretch across decades, even under wildly optimistic assumptions about funding and technical progress. Pessimistic assessments from working engineers suggest some may never achieve operational status, regardless of resources invested. Even assuming major propulsion breakthroughs that current physics permits, but current engineering cannot yet achieve. Minimum journey times to Neptune for any conceivable near-term technology remain measured in years. Not months, not weeks. Years of continuous spacecraft operation in the most unforgiving environment humans have ever attempted to survive, and this is precisely where system reliability becomes the constraint that dominates every other engineering consideration. A crewed Neptune mission would require the most complex spacecraft ever constructed by a substantial margin. Life support systems would need to maintain breathable atmosphere with precise oxygen and carbon dioxide concentrations, potable water recycled with near-perfect efficiency, and stable temperatures within the narrow range human bodies can tolerate. For a crew throughout a journey lasting at least a decade, food production or long-term storage systems would need to sustain multiple astronauts for years beyond any previous mission duration. Radiation shielding would need to protect biological tissues from cosmic rays and solar particle events across exposure periods long enough to cause cumulative damage exceeding safety limits. Medical systems would need to diagnose and treat emergencies, including surgical conditions with no possibility of evacuation, no hope of timely resupply, no access to hospital facilities or specialist physicians. Every single one of these systems would need to function reliably for at least 10 years, probably closer to 20 or 30 years when accounting for mission contingencies, extended orbital operations at Neptune, and return journeys that double total mission duration. And every single one of these systems is built from components that begin degrading the moment they start operating. Consider oxygen generation as a single representative example. The International Space Station uses multiple redundant systems to produce breathable oxygen from water through electrolysis. These systems require regular maintenance by crew members trained in their operation and repair. They require periodic component replacement as parts wear out or fail. They require careful monitoring by engineers, both aboard the station and on the ground, who can diagnose problems as they develop. Spare parts arrive on regular resupply missions launched from Earth barely 400 kilometers below. Entire systems can be upgraded or redesigned based on operational experience. A Neptune mission would have none of these advantages. Resupply missions would be impossible across such distances with any foreseeable propulsion technology. Spare parts for every system that might fail would need to be carried from Earth at launch, adding mass that increases propulsion requirements and extends journey times. Communication delays of over 4 hours each way would prevent real-time troubleshooting and would make ground-based diagnosis and repair guidance agonizingly slow for any situation that evolved faster than 8-hour cycles could address. And the systems would need to function not for months with regular maintenance support, but for decades, with only onboard resources and crew expertise. The mathematical probability of maintaining reliable oxygen generation across a 20-year mission with no external support approaches zero using current technology. This is not pessimistic engineering or excessive caution. This is straightforward statistical calculation based on component failure rates documented across decades of space operations, combined with models of how failure probabilities accumulate when redundant systems must all survive across extended timescales. Component reliability follows well-understood statistical distributions, validated through extensive testing and operational experience. Each system has a mean time between failures, a probability of surviving any given operational period expressed mathematically. For simple components like individual resistors or capacitors, these survival probabilities can remain high across years or even decades under ideal conditions. But complex assemblies combining hundreds or thousands of components into integrated systems see their overall reliability decline. As operational time extends, following mathematical relationships that no clever design can entirely overcome. If a life support system contains 1,000 components, each with 99.9% reliability over 10 years, the system's overall probability of perfect function across that decade drops to roughly 37%. This is not a pessimistic estimate. This is the mathematical consequence of multiplying probabilities across sequential requirements for survival. Each component that must function represents another factor of 0.999. 1,000 such factors compound to approximately 0.37. Add redundancy by including backup systems, and the numbers improve somewhat. But redundant systems add mass that requires more fuel to accelerate. They add complexity that creates new potential failure modes. They add power requirements that strain electrical systems with their own reliability limitations. They add thermal management needs that challenge cooling systems across extended operations. Redundancy represents a trade-off rather than a complete solution. It improves reliability against some failure modes, while introducing new failure modes that would not exist in simpler designs. The Voyager spacecraft provide the most extensive dataset humanity possesses on extreme longevity in space environments. Both probes continue transmitting scientific data from interstellar space more than 46 years after launch. This remarkable achievement might seem to contradict claims about fundamental system reliability limits. Surely, if Voyager can operate for nearly half a century, more modern spacecraft could operate for the 20 or 30 years that Neptune missions require. Closer examination reveals why the Voyager achievements actually support rather than undermine the system reliability constraint. Voyager 1 and 2 were designed with extraordinary engineering margins reflecting the uncertainties of early deep space exploration. Their radioisotope thermoelectric generators carried enough plutonium-238 to provide power for roughly 50 years of gradually declining output, far exceeding the 4-year primary mission timeline. This massive over-design for power systems reflected awareness that accurate predictions of actual power consumption proved difficult before operational experience accumulated. Their electronic systems incorporated redundancy levels that modern spacecraft often cannot afford due to mass and budget constraints imposed by launch vehicle limitations and fiscal realities. Their scientific instruments were selected partly based on radiation, hardness, and long-term reliability characteristics, alongside scientific capability, rejecting otherwise attractive instruments that seemed unlikely to survive multi-year cruise phases. Even with these advantages that most proposed Neptune missions could not replicate, both Voyagers have experienced progressive system degradation that would prove fatal for crewed missions. Several instruments on each spacecraft have failed completely and permanently. Power output has declined to approximately 60% of original levels as plutonium decays following its 87-year half-life, and as thermoelectric converter elements degrade through radiation damage, forcing controllers to shut down heaters and auxiliary systems to conserve remaining electrical power for communications and the most critical scientific instruments. The cosmic ray subsystem on Voyager 2 stopped functioning in 2002. The plasma science experiment on Voyager 1 failed in 2007. Memory systems on both spacecraft have experienced bit flips and data corruption from accumulated radiation damage, requiring creative ground-based workarounds and software patches transmitted across billions of kilometers. Most significantly, for any assessment of crewed mission feasibility, the Voyagers were never intended to support human life. They carry no life support systems, no crew quarters requiring thermal stability, no oxygen generators requiring continuous operation, no water recyclers requiring precise chemical balance, no food storage requiring protection from radiation and temperature extremes, no medical equipment requiring sterile conditions and reliable function, nothing that human survival requires. Their mission involves collecting scientific measurements through instruments that can tolerate partial functionality and transmitting data through communication systems that can operate with degraded performance. A plasma detector operating at reduced sensitivity still provides useful data about the interstellar medium. A camera with partially degraded optics still captures images worth transmitting to Earth. An antenna with diminished gain still sends signals that sensitive receivers can detect. Human bodies are far less tolerant of partial functionality in their support systems. Oxygen generation operating at 80% of designed capacity might provide breathable atmosphere for fewer crew members than the full complement. Carbon dioxide removal at reduced efficiency allows toxic gas accumulation that impairs cognitive function before causing unconsciousness and death. Temperature control with diminished capability creates hotspots or cold zones that become physiologically uninhabitable. Water recycling with contamination breakthrough causes illness that compounds existing stresses. Medical systems with failed diagnostic or treatment components cannot address emergencies that functional equipment would handle routinely. The fundamental lesson from Voyager is not that spacecraft can survive indefinitely in deep space. The lesson is that even the most robustly engineered unmanned systems experience accelerating degradation over multi-decade timescales that would prove fatal to human crews dependent on those systems for survival. Every Neptune mission proposal ever seriously considered by space agencies and their contractors has encountered this same insurmountable barrier when analysis progresses beyond initial concept studies. Engineers can solve the propulsion problem. They can calculate trajectories, design engines, estimate fuel requirements, model gravitational assists, specify tank volumes, and structural masses. Mission planners can map journey phases, identify scientific objectives, outline crew activities, schedule observations and experiments, and develop contingency procedures for foreseeable anomalies. But when system designers attempt to specify the life support equipment required to keep astronauts alive and functional for the full mission duration, and when reliability engineers calculate the probability of that equipment functioning as required across the necessary time span, the mathematics collapse into failure probabilities that no responsible agency could accept for human missions. Neptune remains beyond human reach. Not because the distance is too great in absolute terms. Voyager crossed that distance with 1970s technology, not because propulsion has reached fundamental physical limits. Nuclear thermal and other advanced concepts could reduce journey time substantially, not because humans lack scientific curiosity about the outer solar system or ambition to explore the unknown. Neptune remains beyond reach because machines die, because every component in every system accumulates damage from the moment it begins operating. Because damage accumulation follows statistical patterns that guarantee failure given sufficient time. Because Neptune requires more time than any crewed spacecraft system can reliably survive. The universe imposes constraints that no amount of human ambition can overcome. Light speed limits how fast information can travel across cosmic distances. Thermodynamics limits how efficiently energy can be converted from one form to another. Conservation laws limit what reactions can occur and what products they can yield. And materials science limits how long organized systems can maintain their function against the relentless degradation that entropy imposes on everything that exists. The machines are dying. Every spacecraft begins dying at launch. The question is not whether systems will fail, but when. For Neptune missions, the when arrives before the journey ends. Until that changes, the frozen blue giant remains forever beyond the reach of human hands. What comes next reveals exactly how this dying unfolds. Component by component, system by system. The slow transformation as time turns spacecraft into monuments to entropy's patient victory. Inside every spacecraft floats a silent killer. It weighs nothing. It moves invisibly. It attacks without warning and never relents. This killer is time itself, working through the physical processes that govern all matter in the universe. Understanding how time destroys spacecraft requires examining the microscopic battles occurring in every system, every component, every molecular bond of every machine humanity sends into the darkness between worlds. Electronic systems form the nervous system of any spacecraft. They process commands from mission control. They collect data from scientific instruments. They regulate power distribution across dozens of subsystems. They maintain communication links spanning billions of kilometers. They monitor thousands of parameters that must remain within acceptable ranges for mission success. Modern spacecraft contain millions of transistors, thousands of capacitors, countless resistors, and dense networks of integrated circuits packed into radiation-shielded enclosures. Each of these components begins aging from the moment electrical current first flows through them. Each follows degradation curves that engineers can model statistically but cannot prevent. Capacitors store electrical charge, allowing circuits to smooth power fluctuations and maintain stable operation during transient events. The simplest spacecraft systems require hundreds of capacitors performing this essential function. But the dielectric materials separating capacitor plates slowly break down over time through mechanisms that operate regardless of whether the capacitor is actively switching or sitting dormant. Electrolytic capacitors, commonly used in power conditioning circuits because of their high capacitance to volume ratios, contain liquid electrolyte that gradually evaporates through microscopic seal imperfections that manufacturing processes cannot entirely eliminate. As electrolyte levels drop across years of operation, capacitance decreases and equivalent series resistance rises, degrading circuit performance in ways that cascade through interconnected systems. Eventually, the capacitor fails entirely, often taking surrounding circuits with it, through overcurrent damage or voltage spikes that propagate before protection systems can respond. Transistors face their own degradation pathways. Hot carrier injection occurs when energetic electrons become trapped in gate oxide layers, shifting threshold voltages and degrading switching characteristics. Negative bias temperature instability affects transistors under specific operating conditions, causing progressive performance loss that accumulates with operating hours. Electromigration moves metal atoms within interconnect wires under the influence of current flow, eventually creating voids that increase resistance or open circuits entirely. Each mechanism operates continuously at rates determined by temperature, voltage, current density, and radiation environment. Each contributes to the gradual decline that transforms functional electronics into unreliable systems and eventually into complete failures. In spacecraft operating beyond Earth's protective magnetosphere, additional processes accelerate this natural aging beyond anything terrestrial electronics experience. Cosmic rays, high-energy particles streaming through interstellar space at velocities approaching light speed, constantly bombard electronic components with energies sufficient to penetrate shielding and damage semiconductor structures. The galactic cosmic ray flux increases substantially beyond the heliosphere's protective influence. A Neptune-bound mission would transit through radiation environments significantly more challenging than near-Earth spacecraft encounter, accumulating damage at rates that ground-based testing can only approximate. When a cosmic ray strikes a semiconductor device, it ionizes atoms along its path through the material, creating electron-hole pairs that disrupt normal circuit operation. Single event upsets occur when this ionization flips bits in memory systems, changing stored zeros to ones or vice versa, without any external indication that data corruption has occurred. Error-correcting codes embedded in memory controllers can detect and fix many of these upsets, but error correction consumes processing power that might otherwise perform mission functions, and no practical error correction scheme catches every fault. Some upsets escape detection entirely, corrupting data or program instructions in ways that manifest as anomalous behavior hours or days later when corrupted values finally influence system operations. More severe single-event latch-ups occur when cosmic ray ionization creates parasitic thyristor structures within integrated circuits, establishing current paths that bypass normal transistor controls. These latch-up conditions can destroy entire circuits within milliseconds, through thermal damage if not rapidly detected and interrupted by cutting power to affected components. Spacecraft designers incorporate latch-up protection circuits that monitor current consumption and disconnect power when anomalous draws indicate latch-up conditions, but protection circuits themselves contain components subject to degradation, and protection response times may prove insufficient against particularly severe latch-up events that develop faster than monitoring systems can react. Total ionizing dose represents the cumulative radiation damage that semiconductor materials absorb over extended exposure periods. Unlike single event effects that occur instantaneously during particle impacts, total ionizing dose accumulates gradually as radiation creates trapped charges in oxide layers and interface states at material boundaries. These trapped charges shift transistor characteristics in ways that compound over time, eventually pushing device parameters beyond operational limits. Radiation-hardened electronics designed specifically for space applications can withstand higher total doses than commercial components, but no practical material remains immune to infinite exposure. Every spacecraft carries a radiation budget that mission designers must manage alongside mass budgets, power budgets, and thermal budgets. Exceeding that radiation budget degrades system performance in ways that cannot be repaired or reversed. Confirmed measurements from deep space missions document electronic degradation rates that sometimes exceed pre-launch predictions, despite extensive ground testing programs. The Mars rovers Spirit and Opportunity both experienced flash memory failures linked to radiation damage accumulated during their surface missions. Mission controllers developed workarounds that allowed continued operations with degraded memory systems. But these workarounds consumed engineering resources and reduced mission flexibility. The Cassini spacecraft encountered computer resets attributed to cosmic ray impacts during its 13-year orbital mission around Saturn. Each reset interrupted scientific observations and required recovery procedures that consumed time and ground station resources. The New Horizons mission to Pluto documented elevated radiation effects during its transit through the outer solar system, recording particle flux levels that informed predictions for future outer planet missions. For a crewed Neptune mission lasting 2 decades or more, electronic system reliability presents challenges that current technology cannot adequately address. Even with extensive redundancy, the cumulative probability of critical electronic failures approaches certainty over such extended timelines. Redundant flight computers, redundant navigation sensors, redundant communication systems all help, but all follow the same degradation curves that doom their primary counterparts. Eventually, redundant systems exhaust their backup capacity, leaving missions dependent on degraded primary systems that continue declining toward failure thresholds. Unlike robotic missions where electronic failures merely reduce data collection rates or scientific productivity, crewed missions depend absolutely on electronics for life support operation, navigation accuracy, and crew safety. Electronic failures that robotic missions would record as anomalies and work around could prove fatal for human crews dependent on those systems for survival. Mechanical systems present equally daunting challenges for long-duration missions, though through different degradation mechanisms operating on different timescales. Every moving part in a spacecraft experiences friction, stress, and wear during operation. Reaction wheels that stabilize spacecraft orientation against external disturbances contain bearings that spin at thousands of revolutions per minute for years on end. These bearings gradually degrade even under conditions optimized for longevity. As lubricant films thin, bearing surfaces develop wear tracks, and cage assemblies accumulate fatigue damage from millions of stress cycles. Valves controlling propellant flow through rocket engines contain seals that harden and crack over years of thermal cycling between operational temperatures and cold storage temperatures. Deployment mechanisms designed for single use, such as solar panel hinges or antenna releases, must somehow function reliably after decades of dormancy in conditions that stress their materials in ways that laboratory testing cannot fully replicate. Lubricants pose particular problems for mechanical systems operating in space environments. Standard terrestrial lubricants, formulated for atmospheric operation within narrow temperature ranges, evaporate rapidly when exposed to hard vacuum. The evaporated lubricant molecules migrate through spacecraft interiors, contaminating sensitive optical surfaces with films that degrade instrument performance and coating solar panels with residues that reduce power generation efficiency. Space-rated lubricants formulated specifically for vacuum applications resist evaporation through lower vapor pressures, but these specialized formulations still degrade through other mechanisms that ground-based testing reveals only partially. Some lubricants break down chemically under radiation exposure, producing degradation products that differ from the original lubricant in viscosity, film strength, and surface adhesion. Others become more viscous at the cryogenic temperatures encountered in outer solar system environments, increasing friction forces and wear rates during operations that designers assumed would benefit from lubricant protection. Still others lose effectiveness as their molecular structures fragment under cosmic ray bombardment, degrading performance in ways that correlate poorly with total radiation dose, because damage depends on particle type and energy spectrum, as well as cumulative fluence. The Hubble Space Telescope provides extensively documented examples of mechanical degradation in space, accumulated across more than 3 decades of orbital operations. Despite 5 space shuttle servicing missions that allowed astronauts to repair and upgrade onboard systems, Hubble has experienced continuous mechanical challenges that ground controllers must manage through operational constraints and performance workarounds. Gyroscopes essential for pointing stability have failed at rates exceeding predictions derived from ground qualification testing. The original complement of 6 gyroscopes has dwindled through successive failures, forcing controllers to develop operational modes that require only 3 gyroscopes, then only 2, then only 1 for certain observation types. Solar array. Drive mechanisms that rotate panels to track the sun have required replacement during servicing missions, when degradation exceeded maintenance capabilities. Corrective optics installed during the first servicing mission to compensate for the primary mirror's manufacturing flaw have themselves shown performance degradation over subsequent years of operation. Hubble operates in low Earth orbit approximately 540 kilometers above Earth's surface, protected by Earth's magnetosphere from the worst cosmic ray exposure that deep space missions encounter. It benefits from solar illumination sufficient for solar power generation and thermal management assistance. Most crucially, Hubble received human servicing visits that diagnosed problems through direct inspection, replaced failed or degraded components with new hardware launched from Earth, and upgraded systems with improved technology developed after original construction. A Neptune-bound spacecraft would enjoy none of these advantages that have extended Hubble's operational life far beyond original projections. No servicing missions could reach a Neptune spacecraft. No replacement hardware could be delivered across billions of kilometers. No direct inspection could reveal degradation that telemetry fails to capture. Every mechanical system would need to function without intervention for the complete mission duration, or be backed by redundant systems capable of compensating for their failure. Power systems represent perhaps the most critical reliability constraint for deep space missions, because every other system depends absolutely on continuous electrical power for operation. Solar panels that provide reliable power for near-Earth missions become essentially useless beyond Jupiter's orbit, where sunlight intensity drops to a few % of the levels available near Earth. Neptune receives roughly 1/900th of the solar energy that reaches Earth, making solar power generation effectively impossible without collector areas vastly exceeding practical spacecraft dimensions. A Neptune mission relying on solar power would require collectors measuring kilometers across, introducing structural challenges, pointing requirements, and failure modes that would themselves doom any realistic mission concept. Radioisotope thermoelectric generators offer the only proven alternative for outer solar system power generation, converting heat from radioactive decay directly into electricity through thermoelectric effects without moving parts that wear or fluids that leak. The Voyager spacecraft, launched in 1977, continue operating on radioisotope power more than 46 years later. The Cassini mission orbited Saturn for 13 years on radioisotope power. The New Horizons spacecraft flew past Pluto on radioisotope power and continues transmitting data from the Kuiper Belt. These successes demonstrate that radioisotope systems can provide power for decades under deep space conditions. But thermoelectric generators degrade continuously through multiple mechanisms that compound over operational lifetimes. The radioactive fuel naturally decays according to immutable nuclear physics, reducing heat output at rates determined by the specific isotope's half-life. Plutonium-238, the preferred fuel for space radioisotope systems because of its high power density, favorable radiation characteristics, and long half-life, produces thermal power that drops by roughly 1% annually as plutonium atoms undergo alpha decay. After 20 years of operation, available thermal power has declined by approximately 20% from beginning of life values. This decline is absolutely predictable, absolutely unavoidable, and absolutely independent of any engineering choices mission designers might make. Simultaneously, the thermoelectric elements that convert thermal power to electrical power degrade through mechanisms entirely separate from fuel decay. Semiconductor thermocouples experience progressive performance loss as dopant atoms migrate within their crystal structures under the influence of thermal gradients and electrical currents. This migration changes the electrical characteristics that determine conversion efficiency, reducing power output even when thermal input remains constant. Junction contacts between thermoelectric elements and electrical conductors deteriorate through oxidation at interfaces and interdiffusion between dissimilar materials pressed together at elevated temperatures. Sublimation removes material from thermoelectric element surfaces exposed to vacuum, changing element dimensions and thermal resistances in ways that compound other degradation mechanisms. The net effect of fuel decay and thermoelectric degradation causes electrical output to decline faster than heat production alone would suggest. Voyager 1's electrical power output has dropped from roughly 470 watts at launch to barely 250 watts today, representing declines of approximately 47% despite fuel decay, accounting for only about 40% reduction in thermal power. The additional electrical losses reflect accumulated thermoelectric degradation that cannot be reversed or repaired. Mission controllers have systematically powered down scientific instruments, heaters, and auxiliary systems to conserve remaining electrical capacity for communication and the most essential functions. By approximately 2030, electrical output may become insufficient to maintain any scientific operations whatsoever, ending the Voyager mission not through any dramatic failure, but through the quiet exhaustion of power reserves that degradation has progressively depleted. A crewed Neptune mission would require dramatically higher power levels than robotic probes that can tolerate reduced operations during power-constrained periods. Life support systems alone demand continuous power for air circulation fans, carbon dioxide removal equipment, water recycling systems, and temperature control mechanisms. Interrupting any of these functions, even briefly, creates conditions that threaten crew health or survival. Lighting systems require power for crew activities during work periods. Food preparation equipment requires power for heating or reconstituting stored provisions. Communication systems require power for voice contact with Earth and data transmission. Scientific instruments require power for the observations that justify mission costs. Navigation and attitude control systems require power for course corrections and orientation maintenance. Total continuous power requirements could easily exceed 10 kilowatts, roughly 40 times Voyager's beginning of life output and nearly 100 times Voyager's current degraded output. Providing 10 kilowatts of continuous electrical power from radioisotope sources would require thermal power of 40 to 50 kilowatts, given typical thermoelectric conversion efficiencies of 20 to 25%. Such power levels would require multiple large radioisotope generators containing plutonium inventories measured in hundreds of kilograms. The United States currently produces only about 1 to 2 kilograms of plutonium, 2, 3, 8 annually, a rate so far below Neptune mission requirements that fuel production alone would require decades of preparation. But even assuming adequate fuel supplies, the degradation mathematics become brutal at these power scales. After 20 years of degradation following the same curves Voyager has demonstrated, available electrical power could drop below critical thresholds needed for life support system operation. No amount of engineering cleverness can overcome the fundamental physics of radioactive decay and thermoelectric degradation. No redundancy strategy can replace fuel that has decayed or regenerate thermoelectric elements that have degraded. This brings us back to the real limitation that dominates all mission planning for the outer solar system. Propulsion improvements might shorten journey times, but power system degradation follows its own inexorable timeline that propulsion cannot accelerate or retard. Thermal control systems face their own distinct degradation, challenges that compound power and electronic vulnerabilities. Spacecraft must maintain components within narrow temperature ranges, despite external environments varying from scorching solar exposure. During inner solar system transits to frigid deep space cold at Neptune distances, multilayer insulation blankets, highly reflective radiator surfaces, distributed heater elements, and circulating heat pipe systems work together to manage these thermal extremes through passive and active mechanisms that mission designers balance against mass, power, and complexity constraints. Over years of continuous operation, each thermal control element degrades through mechanisms specific to its design and environment. Multilayer insulation loses effectiveness through atomic oxygen erosion during any transits through low Earth orbit. Micrometeorite perforation that creates thermal leak paths through damaged layers and ultraviolet degradation of polymer films that serve as insulation layer substrates. Radiator surfaces designed to reject waste heat to space lose emissivity as contamination accumulates on their optical surfaces, and specialized coatings degrade through radiation damage and thermal cycling stress. Heater elements fail through thermal fatigue as repeated heating and cooling cycles accumulate stress in resistive wire elements and their electrical connections. Heat pipes designed to transport thermal energy between collection and rejection areas can leak working fluid through microscopic seal failures that grow from pinhole dimensions to complete loss of function. Life support systems for crewed missions introduce complexity levels far beyond anything robotic spacecraft require, multiplying failure modes and degradation pathways proportionally. Each human crew member requires approximately 1 kilogram of oxygen daily for metabolic respiration, typically extracted from water through electrolysis systems or recovered from exhaled carbon dioxide through chemical processing equipment. Water must be recycled from atmospheric humidity, processed urine, and other waste streams with near-complete efficiency to avoid carrying impossibly large water supplies from Earth. Carbon dioxide exhaled by crew members must be continuously removed from cabin atmosphere before concentrations reach levels that impair cognitive function, cause physiological distress, and eventually prove fatal. Each of these life support processes requires complex chemical systems with reaction vessels, catalyst beds, separator membranes, and fluid handling components. Each requires mechanical systems with pumps, fans, valves, and rotating equipment. Each requires electronic systems for monitoring, control, and fault detection. Each requires continuous power supply that cannot be interrupted without immediate consequences for crew safety. Each contains hundreds of potential failure points that would prove fatal within hours or days if not rapidly corrected. Each degrades continuously through the same mechanisms affecting all spacecraft components, following the same statistical distributions that guarantee eventual failure given sufficient operating time. The International Space Station provides the best available data on long-duration life support system performance under actual space operating conditions. Despite continuous maintenance by trained astronaut crews, regular component replacement with new hardware launched from Earth, and real-time support from ground engineering teams monitoring telemetry around the clock, ISS. Life support systems experience frequent failures, requiring immediate workaround development and repair. The station's environmental control and life support system has suffered failures in water recovery units that reclaim water from humidity and urine processing. Carbon dioxide removal assemblies have experienced anomalies requiring backup system activation. Oxygen generation systems have failed in ways requiring crew intervention and component replacement. Atmospheric monitoring equipment has provided erroneous readings requiring calibration adjustments or sensor replacement. ISS benefits from resupply missions arriving every few months carrying replacement components, consumable materials, and upgraded hardware. Failed systems can be repaired using spare parts launched from Earth within weeks of failure identification. Trained crew members perform repairs and maintenance based on real-time guidance from ground controllers who can observe the same telemetry crews. Observe and provide expert recommendations within seconds of any anomaly. A Neptune-bound spacecraft would carry its entire resupply of spare components from the moment of Earth departure. Any failure not anticipated during mission planning through some combination of insufficient component stocking, unanticipated failure mode, or supply depletion through earlier failures could prove completely irrecoverable. Communication delays exceeding 4 hours each way would prevent the real-time troubleshooting collaboration that has repeatedly saved ISS from failure consequences that crew members alone could not have diagnosed or corrected. Every crew member would need training extensive enough to diagnose and repair virtually any conceivable system failure, using only onboard resources, documentation, and expertise. Case studies from long-duration robotic missions illustrate the accelerating failure patterns that statistical reliability models predict, but that pre-launch optimism often discounts. The Cassini mission to Saturn operated for 13 years, from orbital insertion to planned atmospheric entry, far exceeding its 4-year primary mission timeline, through mission extensions that capitalized on surviving system capability. Throughout this extended mission, Cassini experienced progressively frequent anomalies that required engineering workarounds and operational constraints. Reaction wheel performance degraded, requiring modified attitude control approaches. Instrument calibrations drifted from pre-launch references, requiring updated processing algorithms. Software patches accumulated to work around hardware limitations that ground testing had not revealed. The Mars Science Laboratory rover, Curiosity, has operated on the Martian surface for over 11 years. As of this writing, vastly exceeding its original 2-year primary mission timeline. During this extended operation, its aluminum wheels have sustained damage far beyond original design predictions, with holes and tears accumulating through impacts with sharp rocks that wheel design had not adequately anticipated. Its drill mechanism experienced failures that required months of engineering analysis and creative workaround development before drilling operations could resume in modified form. Its nuclear power source has declined following expected degradation curves, reducing available power for mobility and science operations. Despite these accumulating challenges, Curiosity continues productive operations through remarkable engineering adaptability. But Curiosity carries no crew whose lives depend on systems remaining functional. Its failures reduce scientific productivity rather than threatening human survival. The James Webb Space Telescope, launched in late 2021, representing the most complex space science instrument ever deployed. Its operational lifetime was estimated at 5 to 10 years, based on consumable supplies and expected degradation rates. Already, micrometeorite impacts have damaged primary mirror segments beyond pre-launch predictions, reducing optical performance slightly but measurably from beginning of life specifications. Cryogenic cooling systems, essential for infrared observation, continue functioning but follow degradation curves that will eventually limit operational capability, regardless of how carefully controllers manage remaining consumables. Webb represents absolutely cutting-edge space engineering, incorporating lessons from decades of prior missions, yet its designers explicitly acknowledge finite operational duration as fundamental mission characteristic rather than pessimistic assumption. No matter how advanced propulsion technology becomes, the machines themselves cannot survive the journey durations Neptune missions require. Nuclear thermal rockets might cut travel time in half compared to chemical propulsion. Ion drives might improve fuel efficiency by orders of magnitude for cargo delivery missions. Fusion propulsion might someday achieve velocities that would theoretically reach Neptune in years rather than decades. But every propulsion advance must be matched by proportional advances in materials science, component reliability, and system longevity that current research programs are not delivering at required rates. Materials science research continues, producing incremental improvements in radiation-hardened electronics, long-life lubricants, durable thermal control coatings, and reliable power system components. Progress occurs steadily, measured in percentage improvements over previous generation capabilities, rather than the order of magnitude breakthroughs that Neptune mission requirements demand. The gap between what current materials can achieve and what multi-decade crewed missions would require remains vast, showing no signs of closing within foreseeable development timelines. Every deep space mission in recorded history has either failed catastrophically, been intentionally terminated to avoid uncontrolled end of life, or continues operating in progressively degraded condition with capabilities far below original specifications. No spacecraft has ever demonstrated the sustained, uninterrupted, high-reliability operation that multi-decade crewed missions would absolutely require. The accumulated operational data from 5 decades of deep space exploration overwhelmingly suggests that current materials, current designs, and current manufacturing processes cannot achieve the performance levels that human survival over Neptune timescales demands. The machines are dying. They have always been dying. Every spacecraft ever launched began its slow death the moment power first flowed through its circuits. For short missions to nearby destinations lasting months or a few years, this inevitable decay remains manageable through design margins that accommodate expected degradation within mission timelines. For multi-decade journeys to the outer solar system, decay becomes the dominant mission constraint that no amount of propulsion, improvement, trajectory, optimization, or mission planning creativity can overcome. Understanding this decay, in all its mechanisms and manifestations, represents the essential first step toward recognizing why Neptune remains beyond human reach. Not because propulsion technology has reached fundamental limits, because time destroys everything we build, and Neptune requires more time than our machines can survive. Engineers have not surrendered to this reality. They continue developing apparent solutions, redundancy, repair capabilities, autonomous maintenance systems, modular architectures. The next section examines why these promising approaches ultimately fail against the same fundamental barrier they are designed to circumvent. Engineers have spent decades developing solutions to system reliability problems that threaten long-duration space missions. Their approaches appear logical, even elegant in their systematic application of proven principles. Add backup systems for every critical function, include spare components for anticipated failures, design modular architectures that allow failed units to be isolated and replaced. train crews extensively for diagnostic procedures and repair operations, automate failure detection so problems trigger responses before human operators even recognize anomalies, build safety margins into every specification so systems can tolerate degradation without compromising mission success. Every major spacecraft incorporates these strategies in various combinations. Every space agency invests heavily in reliability engineering programs that have accumulated hard-won lessons across decades of operational experience. And yet, despite all this accumulated wisdom and deliberate effort, the fundamental constraint remains unbroken. The paradox emerges when you examine these apparent solutions with rigorous attention to their full implications. Each strategy, intended to improve reliability simultaneously, introduces new failure modes that would not exist in simpler designs. Each adds complexity that creates opportunities for unexpected interactions between subsystems. Each ultimately cannot overcome the mathematics of multi-decade operation that Neptune missions would require. The solutions become part of the problem they were designed to solve. Redundancy represents the most common and most intuitively appealing reliability strategy in spacecraft design philosophy. Critical systems receive backup units that can assume function if primary systems fail. The Space Shuttle main engines used triple redundant flight computers that voted on every command, requiring agreement from at least 2 computers before executing any action. The International Space Station employs redundant life support systems, with backup units ready to activate if primary units experience failures. Deep space probes carry backup scientific instruments and duplicate communication systems that can substitute for failed primary hardware. On paper, redundancy dramatically improves survival probability through straightforward statistical calculations. In practice, the improvement comes with hidden costs that partially or completely offset the apparent benefits. Consider a simplified example that illustrates the essential dynamics. A spacecraft requires a pump to circulate coolant through its thermal control system, maintaining temperatures within acceptable ranges for sensitive electronics. Without this pump, temperatures would drift outside operational limits within hours, causing cascading failures that could prove mission-ending. A single pump designed for space application has 95% probability of surviving 10 years of continuous operation based on component testing and reliability modeling. Mission planners responsible for crew safety consider this probability unacceptably low for human missions, so they install 3 identical pumps in parallel configuration. If any one pump survives and continues operating, the thermal control system maintains function. The probability that at least one pump survives 10 years jumps to 99.9% through basic probability mathematics. 1 minus the probability that all 3 fail equals 1 minus 0.05 cubed, which produces the dramatically improved survival odds. This sounds like a genuine engineering triumph achieved through straightforward application of redundancy principles. But the analysis as presented has overlooked critical factors that significantly complicate the apparent reliability improvement. 3 pumps require power distribution systems capable of supplying 3 times the electrical load of a single pump when all units operate simultaneously during system checks or following failure detection anomalies. Alternatively, the backup pumps operate in unpowered standby mode, requiring startup systems with their own motor controllers, relay switches, and control logic that introduce failure modes absent from continuously operating single-pump designs. The 3 pumps share common coolant lines that carry working fluid between all units and the heat exchangers they serve. These shared lines can develop blockages from contamination, debris, or crystallization that affect all 3 pumps simultaneously, regardless of individual pump health. Vibration generated by one operating pump transmits through mounting structures and fluid connections to neighboring pumps, potentially accelerating bearing wear and seal degradation in units that might otherwise remain healthy. Control systems must continuously monitor pump performance, detect failures through sensor interpretation, and command switchover to backup units when primary pumps show degradation beyond acceptable thresholds. This failure detection and response logic adds electronic complexity with its own reliability characteristics. The switching mechanisms themselves, whether mechanical relays or solid-state power controllers, can fail in ways that prevent backup activation or cause spurious shutdowns of functional primary units. Suddenly, the reliability improvement looks substantially less impressive than initial calculations suggested. The redundant system demonstrates higher survival probability for pump mechanical failures considered in isolation, but the complete system shows lower survival probability for common mode failures affecting all pumps simultaneously. For control system failures that prevent proper backup activation, and for interconnection failures in shared resources that all pumps require, whether net system reliability actually improves compared to a simpler single pump design depends entirely on the relative probabilities of these different failure categories in the specific mission environment and duration under consideration. This pattern repeats with depressing consistency throughout spacecraft system design. Adding redundancy to improve reliability against component failures increases total system mass, which requires more propulsion fuel to achieve the same mission trajectory, which increases propellant tank sizes and feed system complexity, which adds additional potential failure points to systems that must function correctly for mission success. Redundant electronic systems require more electrical power than single-string designs, which demands larger power generation, and storage systems with their own mass penalties and degradation mechanisms, which introduces additional failure modes into power systems that all other systems absolutely depend upon. Backup life support units, capable of maintaining crew survival. If primary units fail, require additional consumable materials, including water for oxygen generation, chemical absorbents for carbon dioxide removal, and filter media for trace contaminant control. These consumables add mass that compounds propulsion requirements and storage complexity, while themselves degrading during the extended timelines Neptune missions would require. The mathematics of redundancy contain a fundamental limit that no engineering approach, however clever, can overcome. As mission duration extends toward the multi-decade timescales Neptune exploration demands, the cumulative probability of common mode failures approaches certainty regardless of how much redundancy designers incorporate into their systems. Common mode failures affect redundant systems simultaneously through mechanisms that redundancy by definition cannot address. They include manufacturing defects present in all units, because all units came from the same production line using the same processes and materials. They include environmental conditions exceeding design limits in ways that stress all units equally, regardless of whether units serve as primaries or backups. They include contamination affecting shared resources that all redundant units depend upon for proper function. They include software errors replicated identically across all backup computers because all computers run the same code, developed through the same design process. No practical redundancy strategy can protect against failures that affect all redundant units equally and simultaneously. For short missions lasting months or a few years, common mode failures remain acceptably improbable because the exposure time limits opportunity for unlikely coincidences to occur. For multi-decade missions to Neptune and back, even initially unlikely common mode failures accumulate to probability levels that mission planners cannot responsibly accept. Cumulative radiation damage affects all electronics, regardless of redundancy, because all electronics share the same radiation environment. Progressive thermal degradation affects all components that share thermal control systems because thermal environments cannot differ between redundant units in practical spacecraft designs. Contamination from material outgassing affects all systems within enclosed spacecraft structures because atmosphere circulates throughout habitable volumes. Micrometeorite damage accumulates on all external surfaces, with probability increasing with time until some impact eventually penetrates protection that all systems rely upon. The Space Shuttle program illustrated these redundancy dynamics with tragic clarity through 2 accidents that killed 14 astronauts despite extensive redundancy in flight-critical systems. Both Challenger and Columbia were destroyed by failure modes that redundancy was never designed to address, and could not have prevented regardless of backup system quantity or quality. Challenger's O-ring failure occurred in solid rocket booster field joints that had no meaningful redundancy because the joint design itself proved fundamentally inadequate for the temperature conditions encountered during that January launch. No backup O-ring could compensate for primary O-ring failure when both rings shared the same joint geometry and thermal environment. Columbia's foam strike damaged thermal protection tiles on the wing leading edge, a system that had no backup capability because spacecraft structures cannot practically incorporate redundant external surfaces. The vehicle depended on single-layer thermal protection that redundancy philosophy could not address. These accidents demonstrated a truth that reliability engineers understand intellectually, but that program pressures sometimes obscure. Redundancy works only against failure types it was specifically designed to counter. It provides no protection whatsoever against failure modes not anticipated during design, against environmental conditions exceeding design assumptions, or against common cause mechanisms that affect all redundant elements simultaneously. All of this still fails because redundancy cannot eliminate the fundamental constraint of materials degradation accumulating over time, regardless of how backup systems are configured. Repair capabilities represent another apparent solution that seems to address reliability limitations through operational flexibility rather than design redundancy. If systems fail during extended missions despite redundancy provisions, trained crew members can diagnose problems through systematic troubleshooting, identify failed components through sensor data and direct inspection, and replace faulty hardware with spare units carried specifically for such contingencies. Repair capability has proven invaluable for space station operations, where astronauts routinely maintain and repair systems that would otherwise limit station lifetime. Spacewalks conducted over decades have replaced failed components on the Hubble Space Telescope and the International Space Station, extending operational lifetimes far beyond what unserviced spacecraft could achieve. Crew members routinely maintain and repair interior systems on ISS, including life support equipment, scientific instruments, and crew comfort provisions. With sufficient spare parts inventories and comprehensive crew training, repair capabilities might seem to solve the reliability problem that redundancy alone cannot fully address. But repair capabilities face their own paradox that becomes increasingly severe as mission distance and duration extend beyond near-Earth operations. Effective repair requires multiple prerequisites that must all be satisfied simultaneously for any repair attempt to succeed. Crews must correctly diagnose the actual failure from symptoms that might indicate multiple possible causes. Appropriate spare parts must be available in onboard inventories for the specific component that actually failed. Suitable tools must exist for accessing the failed component and installing its replacement. The failed component must be physically accessible without requiring disassembly of systems that cannot be safely disturbed. Crew members must have received training applicable to the specific failure encountered. Adequate time must be available for repair activities without compromising other essential mission functions. Missing any single prerequisite renders repair impossible, regardless of how well other prerequisites are satisfied. Deep space missions fundamentally complicate every element of repair capability in ways that compound rather than merely add together. Communication delays prevent real-time guidance from ground controllers who possess expertise and analytical resources, far exceeding what any crew can carry. A Neptune mission would experience communication round-trip times exceeding 8 hours, making the kind of iterative troubleshooting dialogue that has saved numerous missions completely impossible. Ground controllers could not observe telemetry as situations develop, could not suggest diagnostic procedures based on evolving symptoms, could not verify repair procedures before crews execute them. Spare parts must be carried from launch, with mass allocations determined years before the mission encounters actual failures. Components that never fail consume mass budget that might have provided spares for components that fail unexpectedly. Tools designed and tested for anticipated repairs might prove unsuitable for failures that designers did not foresee. Components buried deep within spacecraft structures might require hours of disassembly to access, creating risks that disturbed systems might not reassemble correctly. Crew members cannot possibly train for every conceivable failure scenario in systems containing thousands of components with multiple potential failure modes each. The Apollo 13 mission demonstrated both the remarkable power and the inherent limitations of repair capability under conditions far less challenging than Neptune missions would impose. Creative problem-solving by mission controllers and astronauts working in desperate collaboration saved the crew after an oxygen tank explosion crippled the service module. Controllers on Earth developed improvised procedures for using lunar module resources to sustain crew survival. Astronauts executed complex repair procedures under guidance from experts who could observe telemetry in real time and respond immediately to questions and complications. The mission succeeded because it was only 3 days from Earth, allowing real-time two-way communication that made the crew effectively an extension of ground expertise. Controllers could walk astronauts through unfamiliar procedures step by step, verify results before proceeding to next steps, and adjust approaches instantly when initial attempts proved inadequate. A Neptune mission would face communication delays measured in hours rather than the roughly 1-second delays Apollo 13 experienced. Ground controllers could not walk crews through improvised repairs step by step, because each step would require hours before crews received guidance and hours more before controllers received confirmation of results. The iterative problem-solving that saved Apollo 13 would become impossible across such communication distances. Crews would need to function essentially independently, relying entirely on onboard expertise, procedures, spare parts, and tools regardless of what novel failures they encountered. More fundamentally, repair capability assumes that human crews remain healthy and physically functional throughout mission durations that Neptune exploration would require. Human bodies degrade in space through physiological mechanisms that parallel spacecraft system decay with uncomfortable precision. Bone density decreases by approximately 1 to 2% monthly in microgravity environments as skeletal systems adapt to reduced mechanical loading. Exercise countermeasures can slow this loss, but cannot prevent it entirely over multi-year exposures. Muscle mass declines through atrophy, despite hours of daily exercise because microgravity provides insufficient resistance for maintaining terrestrial muscle tone. Vision deteriorates as fluid redistribution in microgravity affects eye structure and optic nerve function, with some astronauts experiencing permanent vision changes after 6-month ISS expeditions. Immune function weakens under cosmic ray exposure and the stress of long-duration spaceflight, increasing susceptibility to infections and reducing capacity for healing injuries. A crew that has spent 15 years traveling toward Neptune would not possess the same physical capabilities as the crew that departed Earth. Strength for manipulating tools and equipment would have declined substantially despite exercise programs. Dexterity for fine manipulation tasks would have degraded through muscle atrophy and possible neurological effects. Cognitive function for complex problem-solving would have diminished through radiation exposure, psychological stress, and the accumulated effects of sleep disturbances common in long-duration spaceflight. The very crew members expected to perform complex repairs under emergency conditions might lack the physical capability to execute procedures that their younger, healthier selves could have accomplished without difficulty. Even assuming crews maintain adequate physical capability, psychological factors compound reliability challenges for repair operations, requiring clear thinking and careful execution. Isolation from Earth, confinement in limited spacecraft volumes, and separation from family and familiar environments create psychological stress that intensifies progressively over multi-year mission durations. Sleep disturbances affecting cognitive performance have occurred on missions lasting mere months. Depression affecting motivation and initiative has emerged in isolated crews far better supported than Neptune missions could provide. Interpersonal conflicts among crew members have disrupted operations on missions with far larger crews and far shorter durations than Neptune exploration would require. Crews suffering from psychological strain make more errors during complex procedures, respond more slowly to emergencies that demand immediate action, and experience accelerated physical decline as psychological stress compounds physiological degradation. The human components of the overall mission system become progressively less reliable over time through mechanisms that parallel mechanical and electronic degradation with disturbing similarity. Biological systems decay just as material systems decay, and neither degradation process can be prevented through engineering solutions alone, regardless of how clever or comprehensive those solutions might be. Even with unlimited redundancy provisions and extensive repair capabilities, the machines and the humans operating them are dying together through parallel processes that neither can halt. Neither redundancy nor repair can save systems from degradation accumulating over decades. Neither crew health programs nor psychological support can preserve human capabilities indefinitely against biological decline. The fundamental constraint remains regardless of how many backup systems fill cargo manifolds or how many repair procedures fill training curricula. Automation and robotics offer another category of apparent solutions to reliability problems that redundancy and repair cannot fully address. Automated monitoring systems can observe spacecraft health continuously without the fatigue and attention lapses that limit human monitoring effectiveness. Automated failure detection can identify anomalies in milliseconds through comparison of sensor readings against stored parameter limits, triggering responses before human operators even recognize that problems exist. Automated correction systems can initiate recovery procedures without communication delays imposed by ground control involvement. Robotic repair systems might diagnose mechanical failures through systematic sensor interpretation and execute physical repairs that human crews cannot safely access or lack dexterity to perform. Artificial intelligence systems might manage complex spacecraft systems more effectively than human operators by processing vastly more data streams simultaneously and detecting subtle degradation patterns that human perception would miss entirely. These automation technologies offer genuine benefits for specific applications that operational experience has validated. Automated systems have saved multiple missions from failures that would have proven catastrophic without response speeds exceeding human capability. The Spirit and Opportunity Mars rovers survived software glitches that would have destroyed less automated systems through watchdog timers that triggered automatic restarts when primary software became unresponsive. Automated orbital maneuver systems have executed trajectory corrections on deep space missions without requiring ground controller involvement for time-critical burns. Monitoring systems have detected developing problems through trend analysis before anomalies escalated to failures, allowing preventive intervention that preserved mission capability. But automation creates reliability problems of its own that offset benefits in ways that depend heavily on specific implementation details and mission duration. Automated systems require complex software containing millions of lines of code that can harbor errors undiscovered during even the most extensive ground testing programs. Software defects that cause no problems under tested conditions can trigger failures when missions encounter environments or situations that testing did not anticipate. Sensors that feed automated systems with the data they need for decision-making degrade over time through the same mechanisms affecting all spacecraft components, providing increasingly unreliable input to automated logic that cannot distinguish degraded sensor readings from genuine environmental changes. Robotic repair systems capable of useful interventions need power systems, computation systems, mechanical actuators, and spare parts inventories that themselves require maintenance impossible for robots to provide to themselves. The reliability mathematics do not magically change because systems are automated rather than human-operated. Automated systems experience the same electronic degradation from radiation and thermal cycling, the same mechanical wear in actuators and mechanisms, the same software aging from memory leaks and state accumulation as any other complex systems. They are not magic solutions somehow exempt from physics because their complexity takes computational rather than biological form. They are additional systems with additional failure modes that compound overall mission complexity rather than reducing it. Worse than merely adding failure modes, automated systems create entirely new failure categories that simpler architectures would never experience. Software errors can propagate instantly through interconnected systems when malformed data or incorrect commands spread faster than monitoring systems can detect and contain them. Sensor failures can trigger inappropriate automated responses when degraded sensors report conditions requiring action that actual conditions do not warrant. Autonomous systems making decisions based on accumulated sensor errors can take actions that appear logical given their faulty input data, but prove catastrophic in actual situations that differ from what sensors report. The Boeing Starliner capsule experienced software errors during its December 2019 uncrewed test flight that would have caused mission-threatening problems without immediate ground intervention. A mission elapsed time error caused the spacecraft to believe it was at a different flight phase than actual, triggering thruster firings that depleted propellant reserves until ground controllers recognized the anomaly and sent corrective commands. Had this error occurred beyond communication range, allowing rapid ground response, the automated system would have continued its erroneous behavior until propellant exhaustion or some other failure terminated operations. A Neptune mission operating with hours of communication delay could not rely on ground intervention to correct automated system errors before consequences became irreversible. Autonomous vehicle development programs on Earth have demonstrated repeatedly that complex automated systems fail in unexpected ways that developers did not anticipate despite extensive testing. Edge cases that testing never explored trigger behaviors that requirements never specified. Sensor fusion systems that function reliably under most conditions produce dangerous outputs when sensors disagree in ways that fusion algorithms cannot resolve correctly. Adding automation to spacecraft does not eliminate the reliability constraint that limits mission duration. It transforms that constraint into different failure modes, while preserving the fundamental limitation that complex systems cannot function indefinitely, regardless of how they are controlled. The fundamental paradox of automation as a reliability solution is that it shifts failure modes between categories, rather than eliminating failures entirely. Human errors become software errors. Human perception limitations become sensor limitations. Human fatigue and attention degradation become electronic aging and calibration drift. Human psychological decline becomes memory corruption and state divergence. The failure mechanisms change form while the constraint that failures eventually occur and accumulate remains entirely unchanged. Communication delays between Earth and Neptune deserve particular examination because they compound every other reliability challenge through mechanisms that make all other solutions less effective. At Neptune's orbital distance, radio signals traveling at light speed require over 4 hours to traverse the gulf between spacecraft and Earth. Round-trip communication for any interactive exchange takes more than 8 hours. This delay makes real-time monitoring of spacecraft status completely impossible. It makes interactive troubleshooting for novel failures completely impractical. It makes ground-based intervention in developing emergencies completely unachievable. Ground controllers monitoring near-Earth spacecraft can observe telemetry streams in real time, recognizing anomalies as they appear, and responding within seconds when parameters drift outside acceptable ranges. For Neptune missions, controllers would observe telemetry describing spacecraft conditions that existed more than 4 hours ago. Any anomaly visible in telemetry would have already progressed for 4 hours before Earth even received first indication. Any response command sent from Earth would require another 4 hours to reach the spacecraft. Total minimum response time for ground-based intervention would exceed 8 hours, regardless of how quickly controllers recognized problems or formulated responses. 8 hours provides enormous opportunity for cascading failures to propagate through interconnected systems before any corrective action can arrive. Thermal anomalies can cause electronics to fail from overheating. Power system faults can starve critical loads. Software errors can corrupt memory and alter subsequent program execution. The creative improvised problem-solving that ground controllers contributed to saving Apollo 13 Space Station Mir, and numerous other missions experiencing in-flight emergencies becomes completely unavailable when hours separate every exchange of information. Materials science provides the ultimate underlying constraint that no combination of redundancy, repair capability, automation, or any other engineering strategy can overcome. Every spacecraft component is built from materials that obey the same thermodynamic laws governing all matter in the universe. Energy gradients smooth out as systems approach thermal equilibrium. Chemical reactions proceed toward their equilibrium products, regardless of how carefully engineers select stable materials. Organized structures decay toward randomness because the second law of thermodynamics admits no exceptions. No material resists these fundamental thermodynamic tendencies indefinitely. Some materials resist degradation better than others, under specific conditions. Titanium resists corrosion better than steel in oxidizing environments. Ceramics resist thermal degradation better than metals at elevated temperatures. Specialized fluoropolymers resist radiation damage better than conventional plastics. But all materials eventually yield to thermodynamic pressure toward disorder. All materials eventually fail when degradation accumulates beyond the threshold where organized function can persist. The redundancy paradox ultimately reveals a fundamental truth about spacecraft engineering that applies regardless of design philosophy or technology generation. Every strategy developed to improve reliability involves trade-offs that limit its effectiveness. Redundancy adds mass, complexity, and vulnerability to common mode failures while improving resilience against random independent failures. Repair capability requires resources, including spare parts, tools, crew training, and crew health that themselves degrade over extended missions. Automation shifts failure modes between categories without reducing the total failure probability that accumulates over time. Communication delays prevent ground-based intervention that has repeatedly proven essential for resolving novel failures that onboard resources could not address. These strategies genuinely help for short missions to nearby destinations where timelines remain within ranges that materials can survive. They enable space station operations where regular resupply replenishes spare parts, where crew rotation provides fresh personnel, and where emergency evacuation remains possible. They support robotic missions where system degradation reduces scientific return rather than threatening irreplaceable human lives. But they cannot extend human presence to destinations requiring multi-decade journey times that exceed what any combination of reliability strategies can achieve with current or foreseeable technology. Neptune sits beyond the horizon, defined by system reliability constraints. Not because materials scientists have failed to advance understanding of degradation mechanisms, not because space agencies have neglected investment in reliability engineering programs, because physics imposes constraints on how long organized systems can function, and engineering must ultimately respect those constraints, regardless of how desperately mission planners wish to transcend them. The next section examines what this barrier means for humanity's place in the cosmos, and whether any conceivable future development might eventually change the fundamental calculation that currently makes Neptune forever beyond human reach. Stand on Earth tonight and look toward the sky after darkness falls. Trace an imaginary line from the sun outward through the planetary parade that populates our solar system. Mercury orbits closest, a scorched rock with temperatures swinging between extremes that would destroy unprotected equipment within hours. Venus follows, shrouded in clouds of sulfuric acid above a surface hot enough to melt lead, with atmospheric pressure that would crush conventional spacecraft structures. Mars extends the journey outward to a frozen desert, where thin atmosphere and absent magnetic field expose surfaces to unfiltered radiation. Jupiter dominates the middle solar system with radiation belts intense enough to damage electronics within days of close approach. Saturn floats in cold isolation, its rings and moons presenting operational challenges that mission planners have spent decades learning to address. Uranus tips on its side in distant twilight, receiving barely perceptible solar energy at distances that stretch communication and power generation to their practical limits. Each of these worlds presents its own distinct challenges for human exploration. Each demands specific engineering solutions tailored to unique environmental conditions. Each has inspired mission concepts that engineers believe achievable with sufficient development, investment, and operational experience. But none represents an absolute barrier that physics itself forbids humans from crossing. Then comes Neptune. Neptune marks a boundary that differs fundamentally from all destinations, closer to the Sun in ways that transcend mere degree of difficulty. Not because its environment presents more hostile conditions than worlds closer to home. Venus has a hotter, more corrosive atmosphere that would destroy any conceivable crewed lander within minutes of surface contact. Jupiter has more intense radiation belts that would deliver lethal doses to unshielded astronauts during close approaches. Europa has surface ice covering a subsurface ocean that would require drilling technology not yet demonstrated. Neptune's atmosphere, while cold and windy, does not present conditions categorically more challenging than other giant planet atmospheres. Its moons, while poorly understood, do not obviously exceed the difficulty of other outer solar system targets. Neptune's unique barrier is temporal rather than environmental. The time required to reach it exceeds the survival limits of any spacecraft system humans can currently build or can reasonably project building within foreseeable technological development timelines. This temporal barrier operates through mechanisms fundamentally different from environmental barriers that engineering ingenuity might eventually overcome. Every other constraint on Neptune missions ultimately traces back to this fundamental limitation when analyzed with sufficient rigor. Distance creates the timeline that missions must survive. Propulsion technology determines how quickly spacecraft can traverse that distance, but system reliability sets the absolute ceiling on how long any mission can operate before accumulated degradation renders critical systems non-functional. And that ceiling falls decisively short of what Neptune requires. The synthesis becomes unmistakably clear when you examine how secondary constraints interact with system reliability, rather than replacing it as the primary limiting factor. Radiation exposure threatens crew health across multi-year deep space missions through mechanisms that accumulate progressively with exposure duration. Beyond Earth's protective magnetosphere, cosmic rays streaming from galactic sources and solar particle events erupting from our own star-bombarded spacecraft, continuously without the deflection and absorption that planetary magnetic fields provide for surface dwellers. Cumulative radiation dose increases inexorably with mission duration, causing progressive damage to human cells through DNA strand breaks, increasing long-term cancer risk through mechanisms that medical science understands but cannot currently prevent, and potentially causing acute radiation syndrome during intense solar particle events that deep space missions cannot avoid entirely. Mission planners can address radiation exposure through shielding strategies that have been extensively analyzed for various mission concepts. Thick walls of water surrounding crew quarters can absorb incoming radiation through hydrogen content that effectively moderates particle energies. Polyethylene and other hydrogen-rich polymers can provide similar protection with better structural properties than liquid water containment. Specialized materials incorporating boron or other neutron-absorbing elements can address specific radiation components that other shielding materials handle less effectively. Active magnetic shielding systems generating artificial magnetospheres around spacecraft might deflect charged particles away from crew quarters entirely, though such systems remain conceptual. With substantial engineering challenges unresolved, shorter mission profiles that minimize total exposure time reduce cumulative dose through simple time limitation, but every shielding strategy involves mass that spacecraft must carry throughout the journey. Shielding mass adds directly to the total mass that propulsion systems must accelerate and decelerate. Added mass requires more propulsion capability, which itself requires more propellant mass, which compounds the original mass addition through the exponential mathematics of the rocket equation. More powerful engines and larger propellant tanks introduce additional structural requirements and additional components that themselves face reliability constraints. Each addition, intended to address radiation protection, introduces hardware that degrades over the very mission timelines that radiation protection is meant to enable. The optimal radiation protection strategy, therefore, depends fundamentally on system reliability limits, rather than on radiation physics alone. If spacecraft systems could function reliably for 50 years without significant degradation, mission planners might rationally accept longer journey times, using minimum energy trajectories with lighter shielding, trading increased mission duration for reduced launch mass and simplified propulsion requirements. Since systems demonstrably cannot function reliably for multi-decade durations, mission planners who want crew survival must prioritize shorter journey times, even at the cost of accepting higher radiation exposure during those shorter missions. This brings us back to the real limitation underlying all mission architecture decisions. Radiation represents a solved engineering problem. Given sufficient journey time and system longevity to implement known solutions, system reliability prevents those solutions from being practically implemented, because the systems implementing them cannot survive long enough to provide their intended protection. Human lifespan and medical limits present similar constraint patterns that resolve into system reliability when analyzed completely. A 20-year round trip to Neptune would consume roughly 1/4 of a typical human lifespan, even for crew members departing in optimal health at optimal ages. Crew members would age significantly during the journey, potentially developing age-related medical conditions that affect mission performance in ways that pre-mission screening cannot predict with certainty. Cardiovascular disease, cancer, musculoskeletal deterioration, and cognitive decline all become increasingly probable as biological age advances. Medical emergencies requiring hospital-level care, including surgical intervention, intensive monitoring, and specialized pharmaceutical treatment, would be completely untreatable in deep space, regardless of crew training or onboard equipment. Mission planners can address these biological concerns through various strategies that have been analyzed extensively for long-duration missions. Crew selection, emphasizing younger astronauts with exceptional baseline health, could maximize the biological reserve available for tolerating mission stresses. Extensive medical training could enable crew members to handle diagnostic procedures, therapeutic interventions, and even surgical emergencies that would require specialist physicians on Earth. Telemedicine systems connecting crews with Earth-based medical experts could provide specialist consultations for complex cases, though communication delays would limit interactive diagnosis and treatment guidance. Health monitoring systems could track crew vital signs and biomarkers continuously, identifying developing conditions before they become emergencies. But every medical capability depends on equipment that faces the same reliability constraints as all other spacecraft systems. Diagnostic imaging devices contain electronic components that degrade through radiation exposure and thermal cycling. Blood analyzers require reagents that have finite shelf lives regardless of storage conditions. Pharmaceutical supplies expire through chemical degradation processes that cannot be halted entirely even under optimal storage. Surgical robots require mechanical actuators, electronic controls, and sterile supplies that all degrade over extended timelines. Life support systems that maintain the fundamental conditions enabling crew health depend absolutely on components that fail progressively as operating hours accumulate. The medical constraint on Neptune missions is not ultimately about human biology considered in isolation. Human bodies can survive for decades under appropriate environmental conditions, as the entire elderly population of Earth demonstrates daily. The constraint is about maintaining appropriate conditions when the engineered systems providing those conditions cannot themselves survive for the decades that maintaining those conditions would require. Communication delays compound every other constraint on Neptune missions, but ultimately cannot replace system reliability as the primary limiting factor determining mission feasibility. At Neptune's orbital distance, radio signals traveling at light speed require over 4 hours to traverse the void between spacecraft and Earth. Round-trip communication for any interactive exchange takes more than 8 hours at minimum, and orbital geometry can extend this further when Neptune's position places the Sun between spacecraft and ground stations. This communication delay prevents real-time monitoring of spacecraft status by ground controllers. It prevents immediate emergency response when anomalies develop faster than 8-hour command cycles can address. It prevents interactive problem-solving between crew and ground control when novel situations require expertise and analytical resources that exceed onboard capabilities. Mission planners can address communication delays through operational strategies that do not require real-time Earth contact. Autonomous systems can monitor spacecraft health and respond to detected anomalies without waiting for ground commands. Extensive pre-mission training can prepare crews to handle expected emergency scenarios using procedures developed and validated before departure. Asynchronous communication protocols can structure information exchanged to function effectively despite transmission delays. Video messages can maintain psychological connections between crews and families despite the impossibility of real-time conversation. But autonomous systems require reliable electronics that degrade through the same mechanisms affecting all electronic components. Training materials and procedure documentation are stored on data systems that experience memory corruption and storage degradation. Communication equipment including transmitters, receivers, antennas, and signal processing electronics suffers the same reliability constraints as all other spacecraft components. Communication delay mitigation strategies depend entirely on equipment that fails progressively over the extended timelines that make communication delays significant in the first place. Psychological isolation represents perhaps the most fundamentally human constraint on Neptune missions, operating through mechanisms that engineering cannot directly address. Crew members would spend years confined in limited spacecraft volumes with the same small group of individuals, separated from family, friends, and every familiar element of their previous lives by distances and timelines that render normal human relationships impossible to maintain. Even with communication capability, the isolation would exceed anything previous space missions have demanded by enormous margins. The longest space station expeditions have lasted roughly 1 year, with regular crew rotation and continuous real-time communication with Earth. A Neptune mission would extend isolation by factors of 20 or 30 beyond this already demanding baseline. Psychological research, drawing from spaceflight experience, Antarctic winter-over expeditions, submarine deployments, and isolation chamber studies suggest various strategies for mitigating isolation effects. Crew selection can prioritize psychological resilience, stress tolerance, and interpersonal compatibility through screening processes that eliminate candidates showing vulnerability to isolation-induced disorders. Habitat design can maximize privacy within spacecraft volume constraints, providing personal spaces where crew members can temporarily escape group dynamics. Entertainment systems can provide variety and stimulation that counters monotony. Structured work schedules can provide purpose and routine that maintain psychological organization. Communication with Earth, even with delays, can maintain connections that prevent complete psychological separation from human civilization. But psychological resilience itself depends on physical conditions that engineered systems must provide. Crews cannot maintain psychological health if life support systems fail and survival becomes the overwhelming concern. Entertainment systems require electrical power and functional electronics. Communication depends on equipment that must operate reliably across decades. Physical deterioration resulting from life support degradation, medical system failures, or other system malfunctions accelerates psychological decline through mechanisms that no psychological intervention can address. Every secondary constraint examined in detail ultimately defers to system reliability as the primary limiting factor, because every strategy for addressing secondary constraints requires engineered systems that degrade over time following. The same patterns that make system reliability the fundamental barrier. The theoretical maximum mission duration for crewed spacecraft depends on multiple interacting factors that engineering analysis can estimate, though not precisely predict. power system longevity sets one fundamental limit that no other system can exceed. Radioisotope thermoelectric generators using plutonium-238 fuel can provide electrical power for roughly 50 years of progressively diminishing output before production drops below levels required for minimum life support. Operation. This timeline derives from plutonium's 87-year half-life, combined with thermoelectric element degradation that compounds fuel decay. Life support consumable supplies set another limit that recycling technology can extend substantially but not infinitely. Chemical absorbents for carbon dioxide removal saturate and must be replaced or regenerated. Water recycling systems cannot achieve perfect efficiency and gradually lose inventory to leakage and incomplete recovery. Structural integrity limits arise from cumulative radiation damage, embrittling materials, thermal cycling, fatiguing joints and connections, and micrometeorite accumulation gradually perforating and degrading external surfaces. Current engineering experience suggests that optimally designed spacecraft, incorporating every reliability enhancement within practical constraints, might maintain minimum life support capability for perhaps 15 to 20 years with extraordinary redundancy, perfect manufacturing execution, and considerable operational luck. This estimate draws from International Space Station experience, extrapolated to deep space conditions with corrections for unavailable resupply and maintenance. It incorporates Voyager degradation data applied to more complex systems, with appropriate scaling for increased component counts. It includes theoretical modeling of failure accumulation rates validated against long-duration mission databases. The estimate represents best-case performance that actual missions might not achieve, not conservative prediction with margin for unexpected problems. 15 to 20 years of reliable operation is not enough for Neptune missions, regardless of trajectory optimization or propulsion enhancement. A minimum energy trajectory exploiting optimal planetary alignments requires roughly 12 years for a flyby mission that does not stop at Neptune. Orbital insertion, adding capability for extended observation, would extend this to 15 years or more depending on approach velocity and orbit parameters. Return journey, traversing the same distance under similar propulsion constraints, would add another 10 to 15 years. Total round-trip duration approaches 30 years for mission architectures, providing meaningful capability at Neptune, far exceeding the 15 to 20 years that optimistic reliability projections might support. The gap between achievable system longevity and required mission duration explains completely why no space agency in any nation has seriously proposed crewed Neptune missions for implementation. The mathematics simply do not work. Regardless of budgets allocated or schedules extended, you cannot complete a 30-year mission with systems that fail after 20 years any more than you can drive a car 1,000 miles on a tank that holds fuel for 500. This calculation assumes current technology without speculative breakthroughs that might change fundamental parameters. Future advances in various fields might shift these numbers in more favorable directions. But the gap between current capability and Neptune requirements is so large that incremental advances, improving components by typical percentages per development generation, seem entirely insufficient to close it within planning horizons that any current mission planner will live to see implemented. Materials science research advances most directly address the reliability constraint that ultimately limits all deep space missions. More radiation-resistant electronics that tolerate higher cumulative doses before parametric degradation exceeds functional thresholds would extend electronic system lifetimes. More durable mechanical components that resist wear, fatigue, and lubricant degradation under space conditions would extend mechanical system lifetimes. Longer-lasting power systems with slower thermoelectric degradation and more efficient fuel utilization would extend power availability timelines. Each advance in materials science extends potential mission duration by improving the fundamental components from which all systems are constructed. But current research trajectories in materials science suggest decades of continued work before revolutionary improvements might materialize as qualified space hardware. Radiation-hardened electronics improve by small percentages per technology generation through incremental refinements rather than breakthrough innovations. Mechanical component durability improves through evolutionary optimization rather than radical reinvention. Power system efficiency gains come through patient research rather than sudden discovery. The gap between current capability and Neptune requirements remains vast, despite continuous progress, because progress proceeds incrementally, while the gap requires revolutionary closure. Self-healing materials represent one promising research direction that might eventually provide larger capability improvements than incremental optimization can achieve. Some polymers under laboratory investigation can repair cracks automatically through chemical reactions triggered by damage, restoring structural integrity without external intervention. Microencapsulated adhesives embedded in composite materials can fill voids when capsules rupture under stress, compensating for matrix damage that would otherwise propagate to failure. Biological systems throughout nature demonstrate that self-repair mechanisms enable long-term survival in hostile environments, suggesting that equivalent mechanisms might be achievable in engineered materials. Self-healing materials could potentially extend component lifespans by factors of 2 to 5 beyond current levels. If laboratory demonstrations translate successfully to space-qualified hardware, this would theoretically increase maximum mission duration from 20 years to perhaps 40 or 60 years, approaching but perhaps still not reaching Neptune round-trip requirements with adequate margin. But such materials remain experimental, with extensive development required before space qualification becomes feasible. Deployment timelines, even under optimistic projections, measure in decades rather than years. Self-healing mechanisms themselves would face reliability constraints, potentially exhausting healing capacity before mission completion. Nanotechnology and molecular-level repair offer more speculative possibilities that current physics does not obviously forbid, but current engineering cannot remotely approach. In principle, nanoscale robotic systems could repair radiation damage at molecular scales, replacing damaged atoms with functional replacements through precise manipulation. Such systems could potentially maintain components indefinitely by continuously reversing degradation at the level where degradation actually occurs. Biological cells accomplish equivalent feats through enzyme systems that detect and repair DNA damage, suggesting that molecular repair is physically achievable rather than fundamentally impossible. But practical nanotechnology repair systems remain entirely theoretical. With no clear development path from current capabilities to functional implementation, such systems would require power supplies, control systems, raw material supplies, and manufacturing capabilities at nanoscale that no current technology can provide. Even speculative projections place capable molecular repair technology multiple decades in the future, assuming research investments that have not yet been committed. And such systems would themselves require reliability assessment across extended timelines, potentially creating recursive maintenance requirements that compound complexity rather than reducing it. Faster propulsion represents the most commonly proposed solution to long journey time requirements. Addressing the problem by reducing the time that systems must survive rather than extending the time that systems can survive. If spacecraft could reach Neptune in 2 years instead of 12, system reliability constraints would largely disappear as limiting factors, because 2 years falls comfortably within demonstrated capability for crewed missions. Fusion propulsion converting hydrogen to helium through sustained thermonuclear reactions could theoretically achieve exhaust velocities and thrust levels, enabling dramatically reduced transit times. Antimatter propulsion, annihilating matter-antimatter pairs, could theoretically achieve even higher performance if antimatter could be produced and stored in useful quantities. Laser propulsion, accelerating lightweight sails through photon pressure, could theoretically achieve velocities approaching significant fractions of light speed for appropriately designed spacecraft. But none of these advanced propulsion technologies exists in practical form that engineering development could mature to flight readiness within foreseeable timeframes. Fusion propulsion requires solving plasma containment problems that have frustrated physicists for 7 decades of intensive research. The joke that fusion is perpetually 20 years away has been accurate for the past 70 years, with no indication that the next 20 years will differ fundamentally. Antimatter production at current particle accelerator facilities generates mere nanograms at costs exceeding trillions of dollars per gram, quantities and prices separated from practical propulsion requirements by factors of billions. Laser propulsion requires infrastructure investments in orbital power generation and beam direction that would exceed the total cost of all space programs in history, with fundamental questions about beam divergence and sail heating remaining unresolved. Even if revolutionary propulsion somehow became available through breakthrough discoveries not currently anticipated, development timelines would extend beyond foreseeable planning horizons. Propulsion systems must be designed, built, tested and qualified through processes requiring decades for technologies as novel as fusion or antimatter would represent. No crewed mission would fly on propulsion systems without extensive flight heritage, establishing their reliability, which itself requires prior missions accumulating operational experience. More fundamentally, faster propulsion addresses only one variable in a multi-constraint optimization problem. A 2-year journey to Neptune would still require reliable life support, maintaining crew health throughout transit and operations. It would still require radiation, shielding, protecting crews from cosmic ray exposure. It would still require power generation and distribution, supporting all onboard systems. It would still require all the systems that current missions require, facing the same degradation mechanisms across shorter timelines, but with practical mission requirements remaining demanding nonetheless. Propulsion advances help reduce the severity of reliability constraints but cannot substitute for materials science advances, because system reliability constrains mission capability, regardless of how quickly spacecraft can travel. Faster ships that cannot support their crews provide no advantage over slower ships that cannot support their crews. The fundamental physics, limiting material longevity in space environments, trace ultimately to thermodynamic principles that no technology within known physics can circumvent. The second law of thermodynamics guarantees that ordered systems become disordered over time, as entropy increases in closed systems. Energy inputs can temporarily reverse local entropy increases, but maintaining order against thermodynamic pressure toward disorder requires continuous energy expenditure that itself faces thermodynamic efficiency limits. Spacecraft materials are ordered structures whose functionality depends on maintaining that order against continuous disruption. Metal crystals have regular atomic arrangements that provide strength and conductivity. Polymer chains have organized molecular configurations that provide flexibility and insulation. Electronic components have precise structural relationships between conductors, semiconductors, and insulators that provide computational capability. Each ordered arrangement represents a low entropy state maintained against relentless thermodynamic pressure toward higher entropy configurations that would destroy functionality. Space environments constantly inject energy that disrupts the ordered structures spacecraft require for function. Cosmic ray particles break chemical bonds along their ionization tracks. Thermal cycling between solar exposure and shadow stresses, crystal boundaries through differential expansion. Vacuum allows atoms to escape from surfaces through sublimation processes that atmospheric pressure would prevent. Solar ultraviolet radiation degrades polymer chains through photochemical reactions that fragment organized molecules. Each energy input pushes materials toward higher entropy configurations that reduce functionality through mechanisms that obey physics too fundamental to engineer around. Resisting this thermodynamic pressure requires energy expenditure for repair and maintenance that replaces disordered structures with ordered replacements. Living organisms accomplish this through metabolism, continuously rebuilding molecular structures that decay through processes that DNA and enzyme systems orchestrate. Current spacecraft lack equivalent repair capability. They degrade continuously without replacement of damaged structures because they carry no systems capable of reversing molecular-level degradation. Even with repair capability, Thermodynamic limits constrain ultimate longevity in ways that cannot be engineered away entirely. Repair systems require energy to operate. Energy storage and conversion systems themselves degrade through the same thermodynamic processes, affecting all other components. Repair mechanisms themselves need maintenance that other repair mechanisms must provide. No closed system can maintain perfect order indefinitely against thermodynamic pressure, regardless of how cleverly subsystems are designed and interconnected. These physics constraints are not engineering problems awaiting solutions from cleverer engineers. They are fundamental features of physical reality that any technology operating within known physics must respect. We can improve efficiency in resisting degradation. We can extend practical lifespans through better materials and smarter designs. We can reduce degradation rates through environmental management and operational optimization. We cannot eliminate thermodynamic decay because thermodynamics is not a design flaw in the universe, awaiting correction. The universe imposes boundaries on what organized complexity can achieve within physical law. Light speed limits how fast information can transfer between separated locations. Energy conservation limits perpetual motion machines, regardless of how ingeniously mechanisms are designed. Thermodynamics limits how long organized systems can maintain their organization against entropic pressure. Each boundary defines what remains forever impossible, regardless of how technology advances within the space of possibilities that physics permits. Neptune sits beyond the boundary defined by system longevity, substantially beyond where qualitative breakthroughs in fundamental physics or materials science would be required. Breakthroughs not currently anticipated, and potentially not achievable within known physical law. Neptune remains beyond human reach, because cascading system decay is the fundamental reason this destination cannot accommodate human presence. The machines that would carry crews cannot survive long enough. The machines that would sustain crew lives cannot function reliably long enough. The machines that would return crews safely cannot maintain capability long enough. Every component in every system degrades continuously, from the moment of launch through mechanisms that accumulate inexorably over time. By the time any foreseeable spacecraft reached Neptune, its life support systems would have accumulated too many failures to sustain human life regardless of redundancy provisions or repair capabilities. This is not a temporary limitation awaiting technological solution within foreseeable development timelines. This is a fundamental constraint arising from physical law that technology must respect rather than expecting to transcend. Materials obey thermodynamics. Thermodynamics guarantees decay. Decay accumulates over time. Neptune requires more time than decay permits. The machines are dying. They have always been dying from the moment of their creation. And Neptune requires them to live longer than the physics governing their existence allows. 4.5 billion kilometers of empty space, 12 years of minimum journey time. This is the true answer to how long it would take us to reach Neptune. The answer is not 12 years. The answer is not 20 years. The answer is not any number of years. The answer is forever. Because the machines cannot survive. And neither can we.